Hi folks, in this episode of the Microcontroller tutorial series we're going to start kind of a sub-series on digital input using the GPIO pins on our microcontrollers to input basically anything, either ground or VCC. And this is a surprisingly complex topic, believe it or not, so I'm going to split it into multiple episodes. And what I want to start with today is basically I take a little switch like this and connect ground and VCC as potential inputs, and then switch between ground and VCC and output that to microcontroller. It's about as simple as it gets. And once we got this sorted out, we take a look at the more interesting stuff actually, and build a bit of a breadboard to work on this. Looks like this. So I've got a similar switch on a bit of strip board to make it fit on the breadboard. I've got two of my LEDs with built-in series resistors to indicate if I'm switching to low or high, or VCC ground or ground VCC, whatever. And these are LEDs with built-in resistors. So once again, if you try to reproduce these with regular LEDs, don't forget your series resistors. Anything from, I don't know, 220 ohms to about a kilo ohm should be fine. If anything else, grab a 1 kilo ohm resistor and you're on the safe side. Going to connect that to the breadboard, and I'm going to show you, I've changed a couple things with those as well. Let's take a look. Here you see another kind of a change. Taking a wooden board and stuck everything I need onto it using a bit of blue tack. The three breadboards, the programmers, Raspberry Pi, which I've actually replaced with a version 3, which still has overcurrent protection, I found out. And yes, I tested intentionally, didn't do that accidentally. And a basic power supply using two LM317 linear regulators, giving me both 3.3 and 5 volts for whatever I need. And there's yet another change. When you take a look at the breadboards, you see they're wired, well, not differently, but a bit more, because for some of the next episodes, we're going to need more than one LED to work with. And I've already showed you this contraption, which is 8 LEDs plus series resistors plus a 9-pin connector, all on a bit of perf board. This was admittedly painful to solder, but I really wanted to figure out if I could do this. And by now things have got even smaller. These ones here don't use single resistors, but instead I'm using a 8 resistor array here on the underside. So this side, there are the connectors, there's a resistor. If you don't have these resistors stocked, and there's not that much of a reason to do so, actually, you can go with single resistors. And of course, if you don't want to do any SMD soldering, you can use something like this. Again, there's resistor array, 8 3mm through-hole LEDs, or even something like this using separate resistors. And yes, you can also use just regular LEDs like this one I'm using here with built-in resistor, or even with a separate series resistor. Make it a kilo ohm and you'll be on the safe side. So that's a bit of a change. And now here's my switch construction. And the first thing we need for this to work is we need to supply it power. I'll put a caveat in. There's power, and you see the LEDs are either red or green as I flip the switch. Now let's connect that to the microcontrollers, and the obvious way to do this is to connect the output, which I've already found out with the additional wires here, to the microcontrollers, we could do that. And you see the LEDs properly turned off and on. We'll take a look at the software in a moment. But this isn't the smartest thing to do. It's a good idea to put a series resistor. In this case I use 470 ohms, which should be fine, to limit the current going through to the input. And you see it still works with the resistor. Why is that? Well, microcontrollers are using field effect transistors, and they don't really have any significant current going through. Means there's no voltage drop on the resistor because there's no current, and it simply doesn't matter to put it there. What, however, it does is, if we somehow mess up our programming and connect two microcontrollers or whatever together, both pins connect together are configured as output, and we pull one low and the other one high, we basically get a short, and that'll quite likely kill the microcontrollers. Having a resistor in here will limit the current that flows, and we avoid some potential damage. So especially when experimenting, this makes sense. It can be a bit of a problem when we go high frequency, but then the problem is really high frequency, because then the stray capacitance of the board and the resistor form an RC filter, which basically affects a bit the behavior of the entire setup. But for our purposes and a hand toggled switch, it really doesn't matter. So let me wire up the other microcontrollers. And here you go. Now, every time I switch the input, the microcontroller detects it and then changes the output on the LEDs. Nothing fancy. We're going to take a look at the sources in a moment. And just one more thing I wanted to show you, because how did I figure out which pin on the microcontroller is the input pin? And the trick I'm using, well, went to the stationery store, got myself a pack of these beaded swing pins, and all I've done was take 3 of these little blue dots you hopefully see on the boards. I cut these things to length, not with my electronic side cutter. This is steel, so it might be a bit hard on them, just with the standard sort of side cutter feature on a blunt nose. So that's pretty much all there is to it. Not very exciting, but well, the interesting thing about all this really is what we have to do on the software side. And as usual, different microcontroller families do things a bit differently, and well, guess we really need to take a look at these things. Here's the code of our simple program, and it looks different than what we've done before, mostly because I've gone through the trouble of actually making this stuff portable, which actually simplifies life if you want to run things on 3 different microcontrollers anyway. I put all the hardware specific parts into an include file called gpio_input_output.h. We're going to take a look at that in a moment. And the main program with that boils down to: I initialize the microcontroller unit, I initialize the input, initialize the output, and then do an endless loop. And in that endless loop, what I do, I read the input, and depending on if it's non-zero or 0, I output a single byte, either all ones or all zeros to the output port. Question here is, how does that work? Well, let's take a look at that header file. Here's that header file, and it's basically 3 views of the same file, different sections. So what I do is I have a section for the 80 mega using the macro defined by GCC, and for the MSP430. So if I'm compiling it for an MSP430 G2553, this macro is set here, or for the PIC16 F887. This macro isn't set by STCC. STCC doesn't do that, so I had to do that in the makefile myself. But, well, it's basically minus uppercase D and then the name of the macro, and you define it. So if you have never seen that before, take a look at the makefile in the tarball I put on the forum. And then I include some hardware-specific header file, and then I have to initialize the MCU. Now, initializing the MCU, if we do that from the main function, I'm just using a macro init MCU, which is defined but empty for the 80 mega, which disables the watchdog timer for the MSP430. And for the PIC, it's a bit different. We have these 2-bit config words, which are outside the actual running program. We have to set these globally, and we don't need an init MCU do anything, so this is empty again. Output goes to port B, or port 1, or port D, depending on the architecture, and this should be obvious from the previous episodes. Input is different. And one more thing, I'm using notation like this, means that's port D or pin D for input with the 80 mega, and then colon, and then the bit that I'm using. So I'm from port D, I'm using bit 7. Don't need to initialize anything on the 80 mega, and I read input not from port D, but from pin D. Kind of confusing, and yeah, I've been mixing these things up myself. But that's the way how the 80 mega stuff is done. And the nice part, of course, about using a header file like this is there's only one place where you can get it wrong, but then you get it really wrong, and it's reasonably straightforward to figure out what mistake you made. On the MSP430, we don't need to initialize anything either, and I'm using bit 2 on port 2, so it's P2 in, and then bit masking that bit out of there. Not much of a surprise. There is a bit of a surprise with the PIC16, and I'm using port B bit 0 here, which is by default configured not as a digital input pin but as an analog input pin, and that means I have to turn that into a digital input pin, and there is a register here or port here called ANSEL H, analog select high bit, because you have plenty of analog inputs on this microcontroller. And I actually had to clear a bit 4 in this configuration to configure the pin as an input pin. And then it's not pin B like on the Atmel, but it's actually, I read from port B as well. Really confusing is if you play around with both Atmel and PIC microcontrollers at the same time. Anyway, that's all there is to it. So this is really easy. Maybe do something about an input pin and then just read it from whatever you need for the particular microcontroller. As long as we just have a clean binary input, either VCC or ground, that's all there is to it. And most complications come from when we feed some kind of input to a microcontroller that's not as nice. We're going to need a couple episodes to talk about these things because they really occur in the real world. And other than that, we've seen the programming part. It's really just about now knowing what name the input pins are available with from our programs. That's pretty much it. So I've updated the cheat sheet And I'm still thinking about turning it into a web page at some point, but not right now. I'll upload everything to the forum at www.sublette-it.com/bivblog/48. Same place to go if you have comments, questions, whatever. And I guess I just gonna make sure that the recording here worked out, and then gonna start recording the next episode. So see you again soon. Bye.